What's up, guys? I'm Kip. I'm group reporter, ranking. Yeah, let's go over it. So I'm going to be doing a quick review. I'm going to be going over some data that we collected during the lab. I'm going to do some assumptions, calculations. On the right here, this is going to be the Rankine cycle. The heat addition that we're putting into the heat exchanger, that's going to be the liquid propane that we were burning. We're also going to have a pump. We're going to have a condenser. That's going to be the big tower that you saw in the lab. And we also had a turbine. It wasn't that big. It was actually very, very small. You could probably overlook it. All right, let's go to the next one here. So here's some results that we got. The fuel flow versus time, it was pretty steady. We never really adjusted the liquid propane valve throughout. So it was about 5.6 liters per minute throughout the time. Next. We also had the boiler pressure. We tried to keep it about 110 gauge PSI there. In the early stage, it was kind of fluctuating a little bit just because we were messing around with the valve. But towards the end, it stabilized. So I'm going to use 110 PSI gauge when I do the calculations later. Also the voltage, like I said, we were adjusting it very early and then it kind of steadied out around about 6 volts. Current, same situation, then it steadied out about 3.5 amps. I mean, this one was just increasing the whole time, man. So let's use like 240 Celsius. Yeah, okay. We also have the turbine inlet pressure versus the outlet. Obviously, the inlet would have higher pressure than the outlet. We're mechanical engineers here. Yeah, same thing, temperature. Yeah, I'm going to use those. RPM, 1500, same situation early, issues. So this is the results for steady state values. Some the highlighted ones I put in bold, so like the boiler pressure, we kept it at 110 PSI gauge, turbine outlet pressure, turbine inlet, and the steady state water use, we used about 2.1 liters of water throughout the entire experiment there. Next. So I'm going to make some assumptions just so I can tabulate some data. So the first assumption I'm going to make is that the water entering the boiler is saturated liquid, which is pretty fair. The boiler is going to be outputting gas or water vapor. And the water entering the turbine is superheated vapor, which is a fine assumption. If you had any liquid in the turbine, it's just going to kind of destroy it. And water leaving the condenser is saturated liquid, also a pretty fair assumption since the pump can really only pump liquid water. Okay, so using these assumptions, next one please. I tabulated some, interpolated some data here. Man, this was a pain. So you guys appreciate this. All right, let's get to the next one. Also calculated some things like the boiler heat produced, the mass flow rate. We had a very low mass flow rate, about like 0.07 kilograms per second, which is fine. And we also had the efficiency of the boiler was about 32%. It's kind of low. Actually, it might be somewhat high, but the pressure relief valve, a group before us was kind of like messing around with it, so it was kind of broken, so it was leaking steam throughout the entire time. So we had some issues there. Next one. We also calculated the power produced by the turbine, which was about 930 watts. I had some issues with this calculation. It kind of ran my head around, and because when I was calculating the generator efficiency, the power produced by the generator was about 2 watts, which compared to the turbine, we're making 930 watts. So we have an efficiency of 0.2%. Okay, you know, I'm not perfect, right? I could have did something wrong here, but let's blame it on them. Okay, so they had issues. We also did the condenser heat, which is about 17 kilowatts. The pump work, 2.2. So we can predict the entire cycle efficiency if we use the boiler's heat as our QN, subtract the work of the pump. We get an overall efficiency of about 8.3%, which is kind of piss poor. Let's go to the next one here. So conclusions, the Rankine cycle's efficiency was about 8.3%. Comparing this to the ideal efficiency of 20%, it's close enough, but like I said, we had some issues with the pressure relief valve leaking throughout the time. Some of the assumptions I could have made were for an ideal cycle, not necessarily what we were going through. You know, interpolation's hard, and you know, honestly, I'm not perfect, so there's some human error. Okay. Any questions here? Cheers, thanks.